Our speakers for the day are MUJEEB DADARKAR and VIJAY BENEGAL. MUJEEB DADARKAR, sound engineer and co-founder OdBle Consultants, is a well-known name in the music industry. He has been a recording engineer and technical consultant to the audio-video industry since 1983. His experience as a sound engineer has spanned numerous documentaries, advertising, and feature film projects. VIJAY BENEGAL's career, who is also the founder of OdBle Consultants, as an independent sound engineer, has spanned close to 3 decades with experience in diverse sound recording and mixing projects for radio, films, televisions, and music albums. He has recorded for illustrious artists and well-known film recording projects. Vijay is currently touring with Shankar Ehsaan Loy as well as Ustad Zakir Hussein's Cross Currents. May I please ask you to give a big round of applause for our speakers for the session.
Read. So why is it important? Why should we worry about control room acoustics? By the way, we've tried to keep this presentation as non-mathematical as possible, just so that you get the core concepts without undue focus on math. Why is it important? Anybody? Because you need a control room which gives you repeatable results, which means you hear something in that control room, you mix based on that. That mix should sound correct elsewhere. Correct? And what does it involve? The room, the speaker system, and the way that the two of them interact. You do not always have the best speakers in the world, and if you have the best speakers in the world, you don't have the best room in the world. And the two of them together will result in what your control room sounds like. Okay. How to achieve this? There's a lot of misconceptions about what goes into the design of a control room. Acoustics is generally referred to as imperfect science. Why is that? Because we know everything about it, but you can't control everything. Which means no matter how well designed, everybody is always hoping that the room turns out to be neutral. If you're lucky, it turns out to be good. Mostly you end up fixing problems that should not exist to start with, but they happen because of errors along the way, because of things that were not particularly clear from the beginning. Many things are not deterministic. Now the word deterministic is a fancy word. It just means you're not sure that it's always going to turn out like this. Many things are not predictable, which means forget about not being sure. We didn't even know that this was going to happen. You can't predict results in many cases. The design of large rooms is easier than small ones. People don't seem to accept this. I mean, the reasons for this we'll come to eventually. And for small rooms, it's actually impossible to fix all the problems. And especially today's day and age where anybody can set up a little monitoring system and a computer with software that allows you to use as a workstation, the temptation is very high to why can't I mix everything in my own little room? The difficulty with that is that acoustical problems can only be fixed acoustically. And in a small room, it is actually impossible to fix all acoustic problems. So once again, we'll get ahead. Please tell me if I'm going too fast, okay? So you might need an acoustical consultant. Now, why do you need an acoustical consultant? Maybe to help design the room. And what is it that makes them peculiar? Is because they have experience and expertise in many disciplines that are necessary for the design and construction of a control room, which are independent from being a sound engineer. So build a room requires the ability to talk to structural engineers, air conditioning engineers, electrical consultants. It's a big list. To work with architects and interior designers to create a space. So, I mean, usually if somebody drawings and details to people that actually execute the work, and to supervise vendors and contractors, which is for the studio owner, the client, it's one headache less. Anything you want to add over here? This is something that, I mean, we've learnt the hard way, that any contractor cannot be used to build a studio, even if your drawings and designs are correct. The reason is that people that have experience in building studio type construction already know the reasons for accuracy and precision. Commercial contractors, the kind that build offices or do interior decor work, don't understand why it has to be done a particular way. So if your drawing says 30 and 1/8 of an inch, they will say, "Ye kya karne ka 30 inch ka banao." If you say you have to use this kind of ply or this kind of block board, no, but this is cheaper. This is how it goes. So they already know the peculiar techniques involved in construction. They work faster with less supervision, which means you don't have to stand on their head the whole time. And they won't give you high blood pressure because of, no, but we always do it like this. I mean, you may always do it like this, but we want it done like this. So this is, I mean, क्या बोलते हैं, 100 रुपए का काम और 500 रुपए का खून जलाओ. So this is one of the things that may make a big difference. Anything else? Want to go ahead? Okay, so now we come to something that everybody says, soundproofing. Most people don't realize that soundproofing is actually two different things. People will ask, we can buy this type of panel and put it up. My neighbors are complaining, will that help? It will not help, because those panels are not designed for soundproofing. We have this new spray paint. We'll spray it on the walls and, will it help my neighbors complaining? It will not help. It was not designed for that. So there are actually two independent things. One is the concept of isolation, and one is the concept of internal acoustics. They are two different things, although they are sort of related to each other. Any isolation? Talk about isolation.
So what does one consider isolation to be? Isolation essentially means we are trying to prevent sounds from outside the room entering the room, and sounds from inside the room should not go outside. That is what isolation means. And what people tend to misunderstand is that just by doing this, it's not the end of the job. Okay, so first is you have to first keep the inside sounds out. Contain the inside sounds within, and don't let outside sounds enter. Whereas internal acoustics has got to do with what is the quality of the sound that remains within the room. Because if you've blocked all sound from going out, where does it go? It's going to remain within the room. It's going to bounce off the walls. So how do we actually tackle this issue to ensure that the sound that remains within the room sounds good to us, and is, rather our output will sound good to people that listen to it. Yeah, sorry, I should have added there that as far as all this is concerned, we want a neutral sounding room. We do not want something that is sounding exciting. It's like, that's not the kind of stuff that says, oh, this really gets me, I feel excited when I hear the song. It has to be neutral for accuracy. Isolation, we measure this with ratings, with numbers such as STC and NC, that's sound transmission class, and noise criterion. And internal acoustics, we are measured with quantitatively with respect to the spectral response, and reverb. Essentially, RT60 is the reverb, a measurement of how much reverberation is contained within the room.
So we'd rather call it acoustical treatment than soundproofing, because it covers both. And going further, I mean, this shows what happens if sound meets an obstacle. Some of it is reflected, some of it is absorbed, and some of it goes through. So the going through part is the isolation bit, and how much is absorbed versus how much of it is reflected will be internal acoustics. So looking at isolation, people ask questions like this. After we have finished building this studio, will it be 80% soundproof? Now, this is so meaningless as to be stupid, because soundproofing is not waterproofing. Can you imagine a situation where somebody tells you a window is 99% waterproof? What does that mean? It means 100 balti pani bahar gira to 1 balti andar aayega. That's what it means. The client will say, "Arey, mera carpet kharab ho jayega." Then you can promise him 99.9% waterproof, which means 1000 balti pani bahar gira to 1 balti andar aayega. Carpet फिर भी खराब होगा ना. Waterproofing, there are no two ways. It is either waterproof or it's not. With soundproofing, using percentages is foolish. It doesn't mean anything at all. So the mechanism that we actually use is called an STC rating. Stands for sound transmission class. And basically it is a report of the level difference between the outside of the room and the inside of the room. So it's measured using a specific standard. It's called ASTM, which stands for the Association of Sample Test Measurements or Substance Test Measurements. And the standard specifies a particular way of measuring it. And the number that is provided, which is, say, let's say you say STC 30. What that means is there is a 30 dB difference between the sound outside the room and inside the room. So suppose like we have a noisy outside, they are making a lot of noise. We measure that level there, and let's say that level is 80 dB. When you come inside the room, if the level is 50 dB, say, that's STC 30, which means there's a 30 dB difference between the outside and the inside. And then there's an NC rating. The NC rating has to do, it's called noise criterion, NC. It is the residual noise level in decibels measured using a different standard. It's called the ANSI, the American National Standards Institute. They have a spec for it. This is basically, suppose we were to measure ambient noise in this room in a specific way, which separates frequency bands and then assigns weights to them. That's called an NC rating. Now the NC rating can be affected by things other than the STC rating. So let's say you build a control room with STC class 50, which means 50 dB difference between the outside and the inside. It means if your outside world is 80 dB, your inside will be at a level of 30. But it may turn out to be more than that. Why? Because the inside of the room is not only the STC class rating. All the machinery in your control room have fans. Those fans make noise. You have an air conditioning system. That air conditioning system is moving air. That makes noise. All of that adds up, and now it's the result of your STC rating plus all this other stuff that causes an NC rating. So this is what an STC rating chart may look like. You can see there are guidelines there. Do you want to comment on that? Yes. The STC chart. So over there it says 60 plus. That is very expensive isolation. Okay, doing better than that is incredibly expensive. Typically, commercial studios just now have STC ratings of 40 to 50. 55 would be a really good STC rating. Yeah.
Also, you should keep in mind that STC ratings also, it covers the whole frequency spectrum, but that doesn't mean that you're getting the same kind of isolation or same kind of transmission loss across the full spectrum, because some frequencies are absorbed or blocked differently from others. So this eventually becomes an overall number.
And STC ratings came from the acoustical, from the architectural side of the business, from construction, and they tend to ignore low frequencies quite a bit. As far as studio construction is concerned, we have to worry about low frequencies as well. We have to worry about all of them. This is what NC rating charts look like. As you can see there, less than NC 20 is excellent recording studio. 20 to 30 is typically what we spec for a control room. Over here you can see that there are different center band frequencies. The measurements are taken for different frequency bands and then weighted a specific way, and that gives us the NC rating. Isolation is affected by two kinds of sound bleed. One is airborne and one is structure-borne. So airborne obviously is what is transmitted through the air, which is basically doors and windows, air conditioning, whereas structure-borne is what is transmitted through the structure. Concrete, by the way, is a very good insulator of sound. Unfortunately for us, modern construction techniques involve reinforced concrete. Reinforced concrete means there is steel in it. And steel is 15 times better conductor of sound than air. So which means structural sound leakage issues are worse than airborne issues.
Now, in order to achieve good isolation, I mean, there are a number of factors that one has to keep in mind. One of the most important ones would be location. I mean, so if you were to consider something like this really huge, tall building, what would you think that would be a good place to actually locate a studio or have some kind of acoustically treated space? Would it be at the top of the building, in the middle of the building, at the bottom? What would it be? There are a number of... Now, because of the... Yeah. Can anybody tell? This show of hands. Which is the best place? Down, middle, up? Bottom? Bottom. Top. Anybody else? 50-50. Okay, you need to consider the fact that the taller the building, it's almost like as if it's and it's all built of steel, right? So what happens when the wind blows? The structure is going to bend, right? It becomes like a tuning fork. So the higher you are, there is going to be a lot more motion in the oscillation, right? So probably not a higher floor, right? We would much rather go to lower levels. So possibly a basement. Lower floors are good, but basements are probably better. But they are not necessarily always the best idea because there are other factors to consider, such as what other, like for instance, if there's a nearby railway station, then that can transmit sound through the ground. So now if you're in a basement, you're at risk of getting this noise leakage from there. Airports, of course, have a lot of airborne noise. Of course, heavy machinery, same thing, again. If you have a printing press above you, then you're in big trouble. There's nothing you can do about that. No amount of, oh well, let's not get to that yet. And of course, elevators, machinery of various kinds, elevators, pumps, AC compressors, etc., etc. One would imagine that a rural area would be better because it's quieter outside. But what about the noise that you are creating that could bother somebody else? You can't consider that, oh, you leave me alone, but I can bother you. You have to consider that as well. So quiet areas are not always the best.
Okay, so one of the construction techniques used to isolate structural noise is what is called a floating flow. Now this can be done by civil work, which is better, or it can be done by carpentry. That's what a civil floating flow looks like. It's like creating another slab isolated from the actual slab. Or it can be done by carpentry. Carpentry is way more expensive, but you may be forced to do it that way because loading constraints on an existing structure may prevent you from building structural floating flow. Carpentry will not give you as much isolation as actual slab floating flow, but there may not be a choice. For walls as well, you can build isolation walls using civil techniques or by carpentry. That's an example of civil isolation wall. This is done by carpentry. This uses staggered studs so that you have actually two partitions separated by an air gap or by a damping membrane. Same situation, civil is cheaper, but loading may prevent you from doing it that way. Don't forget that columns and beams need to be clad. You have to soundproof columns and beams as well. Because why? Steel is running through them. They conduct from other parts of the building. That shows a column being clad. You can see the steel running inside it. You will also need an isolation ceiling, which is basically a ceiling designed to isolate stuff from the true ceiling, which is above that. That's what an isolation ceiling looks like. So this is not the false ceiling.
It's almost like you're building a room inside another room. You have an existing constructed shell and you're trying to build a room within that. Now, how you isolate this inside room from the outside in order to prevent sound leaking back and forth. So there are many techniques to do it. Some are easier to do, some are more difficult, some are cheaper, some are more expensive.
Go ahead.
This is again one of our one of the biggest problems with keeping noise down within inside the studio is because how is one has to cool the room, because now this room is completely enclosed, so we have to keep it at a temperature that is comfortable for the people working in it as well as the machinery that we are going to use. So we have to have a properly designed air conditioning system. Now, firstly, that would mean that our machinery should be as silent as possible. In the design, also where the machinery is placed, how it is mounted, all these factors affect how much sound is going to be created by the air conditioning system. Then, do we use split air conditioners or do we use window air conditioners? How do we bring the air in? Are we going to have direct feed or are we going to be ducting the systems? This is some of the most important things. We would prefer to have a ducted setup. You can do this with the use of a split air conditioner, which is ductable, like this, as opposed to the indoor unit, which is, of course, every time you use that, you have an artist coming to sing, you have to turn it off because your mic will just pick up that noise. Other systems, you could use a window unit, but if you can duct it, not directly into the room, such as that. Next. Okay, for the HV system, it is imperative that the air conditioning supply and return are separated completely. So we would have a supply duct and a return duct or the exhaust duct separate from each other. We cannot have a system where, like many offices have, where you have for instance, over here we have AC just supply here, and where does the exhaust air go? It just goes out through the ceiling, right? Now, because you can't have two rooms, we're trying to isolate rooms from each other, right? So which means that if I have both my ceiling and on both sides open, it means sound from here can leak over to the other side. So this is why we actually absolutely have to have separate duct systems. And most importantly, we need to have acoustic silencing in the duct itself, because air conditioning means airflow, airflow means turbulence, turbulence means noise. So what the silencers will do is absorbing all that turbulent noise and slowing down the air so that when it comes into the room, it is as soft as possible. So now this is a conflicting situation, because what the AC consultant would like is high efficiency, which means high velocity air, which is exactly opposite of what is required for a quiet room. So this is something that we've had many arguments with air conditioning consultants, but eventually this is what the requirement is, because at the end of the day, that NC rating will rule. So if we say that, okay, we want a room that has NC 25, the AC consultant has to provide a system that will allow us to achieve that. Okay, I think I just said that about efficiency. They want efficient systems, we want lower noise.
The AC consultants are preoccupied with efficiency. which makes sense because they want to be able to cool the room as quickly as possible using the least amount of energy for that situation. Whereas we want as low noise as possible. The two things, they don't shake hands. If you want low noise, you can't have high air velocity. If you don't have high air velocity, the room will not cool quickly. Our response to that is हम लोग AC बंद ही नहीं करते तो cool quickly का सवाल कहाँ पैदा होता है? Where does it matter? रात को ऑफिस बंद होके लोग चले जाते हैं, दूसरे दिन सुबह आके AC ऑन करते हैं. It should get cool quickly. That's why they want high velocity airflow. We don't want high velocity airflow. So if you think about it, efficiency is still important because if you are running your air conditioning system 24 hours a day, you want to pay the least possible bill at the end of the month. So your equipment has to be able to cope with that. So this is basically, it's a continuous fight between the AC consultant and what we need for studios. So doors and windows are the biggest cause of acoustical or air leakage, and that's why they contribute the most towards airborne noise. So the door profiles are peculiar. They have steps in them. You may have seen soundproof doors like that. That's what it looks like. You can see there 3 steps. And the most important thing is that the frame is on all 4 sides. Regular doors do not have the frame at the bottom, which means there will always be an air leak at the bottom. You need to consider sound locks. What is a sound lock? It's basically a room that acts as an air seal between the control room and the outside world. If you do not have space for a sound lock, you can see a sound lock there. Access to the control room is through a little room. This ensures that both doors cannot be open at the same time. Or you have multiple doors. If you can't afford the space for a sound lock, then you have to have 2 doors, like this. The other important thing is that the doors cannot be perforated. You see there are handles. The door lock cannot allow that the handle have a shaft going through the door, because now you have created a hole in the door. So typically these kind of latches are only operatable from one side of the door, so that the shaft doesn't go through all the way. Handles are fitted with screws. The easy approach is either handle rakho, samne se hole drill karo or nut bolt tight karo. You can't do that with these doors. Casement windows, you can't use sliding windows. Sliding windows cannot give you soundproofing. So casement windows means a door which is a window which is hung on a hinge and closes in a frame. That's a studio control room window. Solid or laminated glass. Don't use vacuum sealed glass. Vacuum sealed glasses are designed for commercial construction. The glass itself is very thin. There are 2 sheets of glass with a vacuum gap. So they are better isolation than just a single pane of glass. But you can't use them in control rooms because they vibrate. The glass itself is very thin. Different pane thicknesses. This is something that people forget. You have a control room glass like that. This is the point. Can you see the pointer there? No, on the white is actually. So here's one glass, here's another glass. These 2 glasses should be different thicknesses. Because if they are the same thickness, they are also the same height and width. If they are also the same thickness, they will vibrate at the same frequency. That frequency will pass through. So that's why different thicknesses. The panes are usually angled. One of the reasons is the glass is a reflective surface. You don't want it reflecting straight, you want it reflecting down or up, bounce in some random direction. That's one thing. The other thing is to avoid total internal reflection. If you have 2 parallel panes of glass and you try to see through it, you will see your own reflection. So that's the reason the glasses are angled. Now coming to internal acoustics.
Okay, so one of the measurements or from a technical standpoint, what do we look at when we are considering the internal acoustics of a room? So there are 2 parameters here. One is the spectral response, which is basically what is the quality of the audio spectrum inside the room. Now it has to be measured, so the frequency response, and this is a combination of the construction of the room itself along with the speaker system. So because that's essentially your noise making or noise generating point. So that will interact with the room and create it will sound in a particular way. So we want it to be we're trying to get it to be as neutral as possible. So we have to take measurements for that. The other factor that affects spectral response is the room geometry. Is the room a square? Is it rectangular? Is it uneven? Does it have parallel walls? So room geometry affects the room in a particular way. For instance, if you have parallel walls, you will have sound bouncing back and forth. If the room supports certain specific frequencies based on the dimensions, then you will have a phenomenon that is known as standing waves, also known as room modes. We try to, you can never get away from a room mode. We have to try to minimize the effect of the room mode. Next. If you have multiple room modes which are coincident, which are same frequency, then the room will start resonating at that particular frequency. So we try to eliminate the resonances as much as possible. The next parameter, of course, is our reverb time, RT60, which is the time required for the sound energy to decrease to 60 dB of its original. Now, that after the source emission has stopped. So it could be 15 seconds, depends if you're in a large cathedral, it could be 6 seconds, it could be 1 second, depending on the room. What's next? Again, dependent on room geometry. The shape of the room will affect how much reverberation you will have. And also the quality of the surfaces. I mean, do we have absorptive surfaces? Do we have reflective surfaces? All this will play into how much reverb time is going to be a factor in the room. So spectral response might look something like that. That's like a real-time analyzer that is showing. So as you can see, that got a couple of very large peaks, which we would try to eliminate.
You see the red bits are above the average level mark, which means the room is resonating at those frequencies.
Yeah. And here's another display of like what kind of RT60 this room is going to. It's showing at roughly how much? 400?
0.4 seconds.
0.4 seconds, approximately. So this would be reasonably good as a control room.
Okay, so this is the basic formula. V is equal to n lambda. V is the velocity of sound, n is the frequency, lambda is the wavelength. So every frequency will have a wavelength and it's inversely proportional. The lower the frequency, the bigger the wavelength, the higher the frequency, the shorter the wavelength. Why is this important? Because this defines what happens with room modes. The velocity of sound is approximately 343 meters per second, 1130 feet per second. And it's not constant. It changes depending on where you are on the surface of the earth, what is the exact water vapor, carbon dioxide, nitrogen, oxygen combination of the air and so on.
Temperature also.
Temperature. For room mode calculations, the distance of L from wall to wall will support a wavelength of 2L, which immediately tells you that if you have two parallel walls 10 feet apart from each other, that means lambda becomes 20. 10 feet times 2, 20. And using the velocity of sound, that will give you 55 hertz to 60 hertz is what that room supports. So basically this is how room modes are calculated. That's 3D drawing of a room mode. And room modes can happen at harmonics as well. So you can have the fundamental times 2, times 3, times 4. And if multiple dimensions of the room are similar, coincident, submultiples of each other, then those harmonics start overlapping. And that's when you say that this room sounds terrible because it supports one frequency more dominantly than the others. That's what I just said. Coincident modes cause room resonance. By the way, people have worked out multiple what they call golden ratios, which is if one dimension of the room is 1, The other one, say height is 1, then width should be 1.33 and length should be 2.56. There are other such combinations. Basically what they do is they make sure you don't get coincidences in room modes. You can also do non-parallel walls. So that shows room modes. So you can have them across all the axes. You can have a tangential mode. You can have an oblique mode across corners. This is a terrible room. Why? Because dimensions are very similar to each other. Cuboid rooms, rectangular rooms are usually terrible. That's a very nicely designed space. So you see the outside is still rectangular, but internally the walls have been adjusted so that maybe they are symmetrical, but trapezoidal, pentagonal shapes like these are much better.
Okay, in order to tackle, so what I mentioned earlier about the quality of the sound within the space, within the room that has now been enclosed, we need to tackle that by the use of a number of acoustical devices, one of which is what is called a broadband absorber. Now this is going to absorb sounds that are currently flying around in the room. The other kind of absorber that we could use is something that is tuned for specific frequencies. So broadband absorbers operate across the frequency spectrum. They work well across a number of frequencies, whereas the tuned absorber is specific for a small range. Broadband absorbers, absorb all frequencies whose wavelengths are smaller than 4 times the thickness of the absorber itself.
So as an example, if you have a broadband absorber which is 1 inch thick, absorbent material, it will only absorb frequencies higher than 6K. Why? Because 1 inch times 4 is 6 inches. And 6 inches is roughly the wavelength of, say, a 6K waveform, which means it will absorb everything that is higher than 6K but do nothing for frequencies lower. So which means if you want to absorb 100 Hertz, your broadband absorber has to be about 4 feet thick. Because a 100 Hertz waveform has a length of 11 feet. You get the point. Thin absorbers do nothing for low frequencies. Yeah. They're relatively simple to implement.
They're easy to implement. They do, like you said, like 4 feet if you want to do 100 Hertz. So it occupies a lot of space. So if you want to deal with low frequencies, you're using something else for it. Tuned absorbers only are tuned for a specific range of frequencies that are bothersome. And they are designed specifically for that. And they are complex. There are many types: porous, Helmholtz absorbers, membrane absorbers, and tube traps. Well, because they are designed for specific frequencies, they can also occupy a lot less space, which is also critical. But they tend to be a lot more expensive and probably heavier as well. These are some examples of broadband absorbers. There's one. That's another one. These are your tuned absorbers. This is Helmholtz absorber.
Matkas also work.
Yeah, matkas work as well, yeah.
But you have to find out what frequency they're resonant at. They will only absorb that. That's a membrane. And that's a tube.
And that's a tube trap, yeah.
So you can get these ready-made at pre-decided frequencies, or you can build them custom, which means they have to be designed for those frequencies and so on.
Yeah, because if your room has something that is not in the standard design, then you have to probably have one custom made for yourself.
So this is just a picture that shows the difference between reverberation and echo. So reverb is basically what happens when each reflective surface is not far enough from you to produce an echo. When is it an echo? If it is longer than 100 milliseconds later, then it's an echo. If it's less than that, then it gets clubbed together and gets called reverb. Reverb is usually multiple reflections, wall to wall, wall to ceiling, ceiling to, floor, and so on, and it keeps bouncing around until enough of it is absorbed that you can't hear it anymore. People used to say 0.6 seconds is good for recording studios in the old days. Eventually, people realized that musicians are not happy performing in spaces that don't have a lot of reverb. It sounds very dead and they don't enjoy it. However, if you record in a space that has a lot of reverb, you can't take it out afterwards. So the tendency is to use a space that is more dead than you like. And today we have every conceivable way of creating reverb in the studio using DSP. Today's situation says 1 to 1 seconds for the recording studio side and 0.2 to 0.5 seconds on the control room side. Why don't we want a lot of reverb on the control room side? Because in the control room, you should be hearing the reverb from the studio, not of the control room itself, because that is going to color your perception of what you're doing. So that's a chart that on an analyzer that shows RT60. You can see decaying reflections. This is a chart that shows the difference before treatment and after treatment. As you see, before treatment, it's pretty loud. After treatment, it has come down. The length may not change very much, so the reverb lasts for the same amount of time, but at least it's not uneven.
Okay. For absorptive materials, of course, we have to consider like how much absorption is going to happen. I mean, it depends on the kind of material that we use. So with that, we are using a parameter that's called the absorption coefficient, which is a number between 0 and 1, which defines the absorption, how much absorption is going to happen of the sound. But, okay, a large open window, for instance, these doors are will have an absorption coefficient of 1 because all sound that goes out goes, it doesn't come back, right? So it's just absorbed and gone.
But you can't actually use a large open window because then the neighbors will shout at you.
Because then sound that comes from outside also is absorbed 100%, right? A thick, smooth, concrete walls would be like almost like a mirror, so like almost 100% reflective. And of course, this is a character of materials, different materials, and it is not, it's different for different frequency bands. So just because something is absorbing well at high frequencies does not mean it will do the same for you at low frequencies. So the charts generally would look like this. You see different octave bands for different materials and shows. So the closer to 1 you get, the better means the better absorption you have.
You see, this says at 8K absorption coefficient of 1. That means this is absorbing 8K completely. Same with 4K, same with 2K, 1K, 500. 250 it absorbs only. Okay. So we're going to rush through. We're falling short of time. So this is what a diffuser does. It bounces things off in random directions instead of, specular reflection like that one. This is what diffusers look like. There are different kinds. All of them, the purpose is to scatter sound. Diffraction is things bending around other objects, sound waves bending. This depends on, obviously, the size of the object with respect to the wavelength. So this is why sound can get around an obstacle or through an obstacle, even through a small hole. This causes an issue called edge diffraction with monitor speakers, where at the edge of the speakers you get secondary waves. These will cause cancellations and blurring. It's because the dimensions to each corner or each edge are not the same. This is, we choose between stand-mounted monitors, which are convenient, simple. Main monitor should be as far back as possible, near fields as close to the desk so that you don't get reflected sound from the walls. These are all monitors mounted on stands. This, by the way, is a very cluttered control room. Edge diffraction issues can only be solved by the designer of the speakers, which explains why you have some speakers like this. You see the rounded edges so that you don't have edge diffraction issues. Or you can soffit mount monitors, which is basically cut a hole in a large wall and fit the speaker there. These have the least problems, they have the highest efficiency, But it's not a partition with a hole in it and a speaker stuck in that. It's actually a part of the design of the room. That's what the design looks like. It needs to be massive, so concrete constructions are common. Monitors with rear ports, you have to worry about where that rear air is going to go. If they have amp modules on the back, they have to be remotely located, because otherwise, how is the heat going to be extracted? They're very expensive to do, very much heavier, and they drive room modes very strongly. So your absorption in the room and your room size calculations had better be correct. This is what a proper soffit mount looks like. You see, the surface is flush with the wall. So there is software for room simulation which allows you to visualize rooms before they are built in terms of what they will do acoustically.
So we have different types of software. One is Ease by AFMG. There is Cat Acoustics. There is Odeon. Where is Odeon? Yeah, Odeon room acoustic software. And they produce outputs such as these. I mean, you have all kinds of simulations and showing you how the sound is going to be distributed across the room. But thing to note is that these are much better for designing large spaces and not so good for smaller rooms, like for a studio or whatever. And these softwares are not cheap. They're quite very expensive, because they have to run all kinds of mathematical calculations for. Then we have analysis software for judging what the room is going to be like once it's built. So that is real-time measurements. This is a real-time hardware, real-time analyzer, which is not much used anymore. We have, or you could use a handheld device such as the Phonic. Some of the finest test equipment is built by Brule & Care. Applied
Audio Precision.
Audio Precision, sorry.
They all have software variants of their analyzers now. And this is one of the most popular. And this is what reports from these software analyzers can look like. Speaker calibration or room tuning, you can't, I mean, this is actually wrong. You can't tune a room except acoustically. What you're doing is correcting it electronically. So that can be done using hardware, such as crossovers or speaker management systems or programmable EQs or room correction systems designed for that. This is what the hardware looks like from various companies. There's also dedicated things like this. So this is from IK Multimedia, that's Mini DSP. Or you can use software. And software is two types. One is, some manufacturers have inbuilt DSP in their active monitors, and they'll give you calibration software. This is the approach that Genelec takes. They have something called GLM. And then there's third-party calibration software that runs as a background service in your computer. And that's what SonarWorks is one of the most popular. And you can correct, responses that look like that and make them look like this. Okay. I don't think we have time for questions, but I mean, just in case, we'll see. Yes.
Yes, Tim.
Give him a mic. When we are talking about isolation in a room, is it only considered, like, can it be only considered while making the room or construction phase? Or after tuning of the room also we can add to the isolation?
No, you can't fix isolation after the room is constructed. Because what are you going to do? Are you going to add more walls?
Essentially.
You see, everything changes. The dimensions of your room will change. What all stuff you're going to put there now has to be relocated. Your services will change, air conditioning, all of that. So the only time you can worry about isolation is when the room is being built. Let's say you have an existing room, you want to isolate it more, you're going to have to build a double wall inside. But this is the only chance you get to do it.
So are there any books we can refer to?
Oh, there is a lot of information available on the net. There are many books, all of which are pretty good, but they're usually too complicated, to understand for the average, musician or recording engineer who's setting up his home studio. So this is where the difficulty lies.
Thank you so much, sir.
Okay, thanks everybody. We are unfortunately out of time, so thank you.
Mujeeb sir, Vijay sir, you've been marvelous today. Please give a big round of applause for our speakers. So may I please ask you to stay back on the stage for a moment as I present the token of appreciation to you.